So we're going to get started. I have to say that this first session, Grand Challenge number 1, we're calling it, on fossil fuels and decarbonizing fossil fuels. Actually, I'm going to give credit to Mark Northam, our moderator for this session, for coming up with grand challenges when we had our steering committee. So thank you, Mark, for giving us some great ideas and bringing your speakers that you know will cover this very thoroughly, huh? You all have bios, very thorough bios, and their titles and their organizations in your printed program. And those that are watching live stream, you can see it on the website. I'm going to hand this off to Mark Northam from the University of Wyoming. Please give him a warm welcome.
Thank you, Maury, and I will introduce my panel after I've gone through my 27 pages of introduction so that it's closer to when they actually speak and you can remember who they are. So the number one grand challenge, and this is number one for us in Wyoming because it is really having an impact on our economy, and that is decarbonizing fossil fuels. As you all know, Wyoming is an energy state. We're the number one producer of coal, number 3 in natural gas, and number 8 in petroleum, all of which are very important to our economy. There's a growing global consensus that human activities are forcing climate change and that we're falling behind in our efforts to prevent temperature rise from exceeding 2 degrees centigrade. There's also general consensus among scientists and policymakers that emissions of carbon dioxide from the combustion of fossil fuels are a contributing factor in forcing anthropogenic global warming. There is still some vigorous debate about the case, but markets have generally sided with the affirmative case. To control emissions of carbon dioxide, technology solutions are being sought for decarbonizing fossil fuel, either by decarbonizing the fuel prior to their combustion or by removing carbon dioxide from flue gas after their combustion and either utilizing the carbon dioxide to create products or storing it in the subsurface. The latter process, that is storing it in the subsurface, has become known, the process of capturing it and storing it has become known as carbon capture, utilization, and storage. And everywhere you go these days, you hear people talking about CCUS. Carbon capture and storage have been the subject of research for lots of years. I've personally been involved with it for 25 years. Carbon dioxide utilization is relatively young and is less well developed. And in fact, the slide that I chose to put up first is a general scheme. How do I make it go from there to, oh, it's over there, okay. Sorry, I thought it was going to be behind us for some reason. It's a general scheme for the types of processes that need to take place in order to take that carbon dioxide coming out of the stack of the power plant and turn it into something that is not going to end up in the atmosphere. Carbon capture and storage is technically feasible today, although the capital cost and energy requirements are high. The economics do not currently support broad application, though there are several demonstration projects that have been implemented. 2 of the best known and most successful are Sask Power's Boundary Dam project in Estevan, Saskatchewan, which is shown in this diagram. That particular plant is capturing the carbon dioxide emitted from a 115 megawatt unit in the power plant. It's capable of capturing up to 1.3 million tons of CO2 a year, and it's capable of reducing sulfur dioxide and by 100% and carbon dioxide by 90%. All of the carbon dioxide that is captured is compressed and sent to an oil field for enhanced oil recovery. Oh, the yellow circle on that diagram is the carbon capture unit that was built as a bolt-on to the plant, and you can see the duct that is taking the emissions from I believe it's Unit 3, to the carbon capture facility. The second one that is quite well known and successful is the Petronova WA Parish plant that is owned and operated by NRG. This plant is southwest of Houston, Texas, and again, I've circled the carbon capture unit in yellow. That plant is capable of capturing 1.4 million tons of carbon dioxide a year, and it's been operating since January of this year, and that CO2 is also going for enhanced oil recovery. So, technologies are capable, are ready. They're being demonstrated, but again, there are lots of challenges that remain in carbon capture, utilization, and storage as being a carbon management process. And so we're going to hear today from this first panel, who are all experts in the field of CCUS. Our first speaker is going to be Jennifer Wilcox. She is an associate professor of chemical and geological engineering at the Colorado School of Mines. She got her PhD in chemical engineering from the University of Arizona. Her research group is focusing on trace metal and CO2 capture. In her career, she has served on a number of committees, including the National Academy of Sciences and American Physical Society to assess CO2 capture methods and their impacts on climate. She's also the author of the first textbook on carbon capture, which was published in 2012. Second speaker is Kip Coddington. He's a director of energy economics and public policy at the School of Energy Resources at the University of Wyoming, where I also am employed. He has degrees in chemical engineering and law from Purdue and Georgetown University. He's got 2 decades of experience in helping fossil and renewable energy companies address challenging energy, environmental, and climate issues. He's a member of the National Coal Council Leadership Committee and chaired the National Coal Council's 2016 report on utilization of CO2. Our third speaker is Larry Baxter, professor of chemical engineering at Brigham Young University. He has bachelor's and PhD degrees in chemical engineering. He's also the co-founder and technical director of Sustainable Energy Solutions, a company that is focused on commercializing cryogenic carbon capture technology. His sustainable energy-focused research involves carbon capture, energy storage, biomass, and fossil fuel processing and nuclear energy. Larry joined Brigham Young in 2000 after 14 years at Sandia National Lab. So I'd like to now invite our first speaker, Jennifer Wilcox, to either come to the podium or speak there. There you go. Thank you.
Thank you for the introduction, Mark, and thank you also for the organizers of this meeting to invite me here today. So what I wanted to do in my 10 minutes is first just get us all on the same page in terms of CO2 emissions. And for those of us that are from the US, the lifestyles that we lead in the United States are very intense in terms of energy. And so to give you an idea, we have a little over 300 million people in the US, and the average per person CO2 emissions per year is about 16 tons of CO2. And you may ask, what is the equivalent of 16 tons? And so to give you an idea of scale, this is an entire family of African elephants. And for those of you, in case you just want to learn something today, the difference between African elephants and Indian elephants, you can look at these elephants and the shape of their ears, looks like the shape of the continent of Africa. So if you learn anything, it's the difference between those types of elephants here today. But thinking about a different country, so China, their population is pretty significant, about 1.3 billion, but the lifestyles that they have are not as energy intensive as those of us in the United States. And so per person, on average, they emit on the order of about 7 tons of CO2 per year. This example that I'm showing next is associated with the CO2 emissions associated with a flight that I took recently. So SFO to Boston round trip is about a ton of CO2 just in that flight alone. If I chose to drive that distance, so the drive, if I chose with a Toyota Prius, it's about 0.8 tons of CO2. Or suppose I chose to drive that distance with a BMW convertible, it'd be about double that, about 1.5 tons of CO2. So it gives you an idea of scale in terms of CO2 emissions. So the work that I do in my research group is on developing strategies for separating CO2, whether it's from a point source like a coal-fired power plant or whether it's the direct removal from the atmosphere. We're interested in all of the above. And so there are three, as a chemical engineer, we think of three primary separation techniques for CO2. One could be a solid sorbent, similar to how your Brita filter works when it's filtering water and purifying it. Another could be a solvent, so like a liquid chemical. So the images that Mark was showing earlier of those power plants that are doing it on scale, demonstration plants, are using an amine solvent-based approach to do that. A third would be membrane separations. And so we actually look at all of those different technologies in my research group at the Colorado School of Mines. But suppose I took one technology. Suppose I took, say, activated carbon to separate CO2 from the flue gas of a coal-fired power plant. If I chose that technology and I just thought of the individual footprint of each of us in this room, so again, going back to 16 tons of CO2 per year, the next question I have is how much material do you think it will take to capture each of our emissions? So each one of us is responsible for the equivalent of a family of elephants. So if you think of the mammal family, how much material do you actually think it would capture the amount of CO2 you generate per person each year? Any guesses? What's the largest mammal you can think of? Yeah, so it turns out the actual amount of material to capture that amount of carbon that we're responsible for per person is the equivalent of a blue whale. And that's based upon the fact that you look at how much CO2 can you actually fit in a given material. This is the kind of loading and the capacity these materials have for CO2. And so what this is telling us is, number one, gives us an idea of the scale, but number two, anything you use to separate CO2, you have to be able to recycle it. It's not going to be a once-through process. You would generate way too many blue whales in a given year per person in order to do that. And we simply don't have enough storage above the ground anyway to do that. So the first message really that I wanted to tell you about is appreciating the scale of CO2 emissions and associated with really the intense energy lifestyles that we lead as Americans. And so along that message, I teach a course on carbon capture and storage. And one of the first questions that students ask me is, why can't we just take all the CO2 and turn it into something useful? And it kind of goes back to what we already talked about in terms of scale. But the other piece is that if you look at all of the chemicals that we produce worldwide, and I'm not talking about chemicals that you would actually use CO2 for feedstock for, such as different plastics and things like that, but all chemicals, sulfuric acid, nitrogen, everything. What I'm showing here is that wedge is the emissions compared to, or actually that wedge is the utilization potential of CO2 compared to all of our emissions. So that tiny wedge is the scale of our chemical industry worldwide. And everything else is the emissions. And so even if you could turn CO2 into something useful, the scale of which that exists, that use exists, that market exists, pales in comparison to the actual emissions of CO2. The second message that I wanted to point out, and this really speaks to the nature of this panel today, is decarbonizing fossil fuels. But where does CO2 come from? And so to give you an idea of the breakdown of CO2 emissions, mostly our CO2 from the energy sector is from coal and natural gas-fired power plants for electricity generation. But then there's also this other aspect, the transportation sector. And mostly that's petroleum-based. And so something that's really important is to understand the top priority should always be mitigating CO2. So in other words, starting with coal and natural gas-fired power plants, mostly because the concentration of CO2 in those emissions is greater than it is, say, from the transportation sector. Once you put CO2 in the atmosphere, it's very difficult to do the separation. We have about 1 billion cars on the planet today. Each one of those is an individual emitter of CO2. And so capturing CO2 from the transportation sector is actually really difficult. There are solutions. We can talk about those. Maybe there'll be some questions about that. But really the primary source of CO2 emissions are from coal and natural gas-fired power plants. And so what I'm showing here is the percentages. The third message that I wanted to point out today is, again, mitigating CO2, and we're not doing enough of this today. And so if you look, for instance, at the number of demonstration scale projects, and Larry talked about a few of these, or I'm sorry, Mark, talked about a few of these, the Global CCS Institute lists about 22 projects that are ongoing today. The scale of these, as was mentioned before, is about 1 million tons of CO2 per year. Again, if we think about the scale of global emissions, it's on the order of about 35 gigatons. So these scales are very different. There's predictions that we need at least 100 more of these kinds of projects, or 1,000, up to 1,000 more to actually make an impact in terms of mitigation. And this is the example of the three primary projects that are ongoing, that are Boundary Dam, Kemper, and Petronova. One thing I just want to point out is the Kemper project is something that was envisioned to be really the first clean coal project. But one of the issues associated with that is it wasn't a retrofit. It was an actual new plant. So you can see in the final line item below, the actual cost of the project was significantly greater than what was originally projected. So this plant actually is not continuing in terms of carbon capture anymore. But the Petronova, I would say, is a success story, and so is the Boundary Dam. But I think that the important thing to point out here is that in all of these, the CO2 is being effectively separated, but the CO2 is also being used for enhanced oil recovery, because there's really just not a driving force in terms of policy to ultimately sequester the CO2 permanently in the earth today. But there is a driving force in terms of economics, for instance, to use the CO2 for enhanced oil recovery. The message number 4 that I wanted to point out is associated with negative emissions. And so this is a plot that was generated in terms of looking at preventing 2 degrees C warming by 2100. And the pathway to doing that is not simply mitigation alone. It used to be mitigation alone, that we could get there just by avoiding CO2 emissions in the atmosphere in the first place. Unfortunately, that's not the trend today. So if we keep emitting CO2 at the rate we're doing today, and not doing the mitigation at the scale that it needs to take place, then negative emissions are going to have to be part of the future portfolio of solutions to preventing 2 degrees C warming by 2100. Negative emission strategies are exactly what I was saying before, which is difficult. It means pulling CO2 out of the atmosphere, which is very difficult to do given that CO2 concentration in the atmosphere is 400 parts per million, where CO2 in the exhaust of, say, a coal-fired power plant is on the order of 12%. So the more dilute a gas mixture is, the more difficult it is to do the separation process. So there's different techniques, for instance, bioenergy with reliable carbon capture and storage. There's direct air capture with reliable storage of CO2. And those are some of the strategies that are being included in these global climate assessment models. This is a little bit of a complicated plot, but what it's showing on the x-axis is CO2 concentration. And as you move to the right, you're looking at the CO2 being more and more concentrated given that technology. If you look at the y-axis, this is the minimum work. So that's a thermodynamic parameter. It's associated with the separation of CO2 from a given gas mixture. At the very top would be taking CO2 out of the atmosphere, which again is 400 parts per million. As you move your way down, natural gas-fired power plants, the exhaust is on the order of about 5% CO2, so it's a little bit easier to do that than, say, from air. Keep moving down, and you get coal combustion, where it's anywhere between 12–14%. And then finally, in a gasification process where you have the greatest driving force of CO2, it's the easiest of the separations, but it's also the most costly in terms of building, which goes back to the Kemper plant that I showed you before. And so the point of all of this is that mitigation is key, and we've been avoiding having to do something like direct air capture, which clearly is thermodynamically prohibitive. But again, if we want to prevent 2 degrees C warming by 2100, we might have to be doing some amount of that direct air capture, which is going to be costly. Finally, this is my last message that I want to leave you with. We need everything, and we need it now, essentially. We need fuel switching. We need carbon capture and reliable storage. We need renewables. We need some component of negative emissions. We need all of these things. And believe it or not, all of the technologies exist today. We can do them. A lot of this really, in terms of moving forward, has to do with policy, putting a price on carbon and putting a price on the emissions. And public acceptance and education associated with geologic storage and what the implications are of that. And so it's not that the technology isn't here and that it's not available or that it's even too expensive. Those, to me, in my opinion, aren't the things that are preventing these technologies from moving forward. And with that, I'm the next speaker.
Thank you, Jen. Kip, your turn.
Much. I think this mic is working. Mark, I wanted to thank you, my fellow panelists, and CSU. It's a privilege to be here. So I'm going to show my age. I know that old game show called Name That Tune, so I can give my presentation in 5 minutes, and I don't have any slides, and I'm going to keep it topical and light, and then I think we'll have an interesting Q&A. So without slides, I just wanted to cover off four brief topics. First, why we're talking about carbon capture and storage. I want to add a little bit about the state of the technology. Thirdly, talk a little bit about policy, and then the importance of this technology for the Rocky Mountain region. First of all, why are we talking about carbon capture and storage? We're talking about carbon capture and storage because if you believe that fossil fuels are going to continue to be used for the foreseeable future, then any number of experts have said that carbon capture and storage is one of those technologies, one of those wedges that's going to have to pencil at scale in order to enable achievement of the 2050 Paris goals. And we all know what the 2050 Paris goals are. It's about an 83% reduction in greenhouse gas emissions, which the practical result of that is the decarbonization of all fossil fuels, including natural gas. So, of course, there is fuel switching going on now from coal to natural gas, but eventually the carbon is going to have to come out of the natural gas as well. So that's why we're talking about this. This is not an esoteric topic. This is a technology that any number of experts around the world, with the support of many environmentalists, have said that we need. That's point number one. Point number two, in terms of the status of the technology, there is tremendous confidence in it. From the source to transportation to the sink. On the source side, as a prior speaker mentioned, not all CO2 sources are the same. You co-produce CO2 with natural gas. There are CO2 streams in refineries. There are CO2 streams in cement plants, all of which are relatively easy to separate, quote unquote. Then on the other side of the spectrum is trying to take CO2 out of flue gas, and the economics of that are more challenging, but even those economics are improving. In terms of the transportation of CO2, there's tremendous confidence of that. The CO2 is typically compressed about 2,000 psi. You put it in a pipeline network, and indeed there's an existing CO2 pipeline network in Wyoming, Colorado, and Texas that's moving relatively large volumes of CO2, largely for enhanced oil recovery. On the storage side, we've heard reference to enhanced oil recovery. CO2, whether you know it or not, actually is, I think it's 17 or 18% of U.S. domestic oil production is produced by the injection of CO2. A lot of this work is going on in Texas, in the Permian Basin. There's also a significant amount of activity in this area going on in the state of Wyoming. And that CO2 is injected. It acts like a detergent, sweeps additional volumes of oil out, and that CO2 is stored as part of that process. So on the subsurface side, there's any number of geologists and reservoir engineers that would also say there's great confidence in this technology. And also keep in mind, from the enhanced oil recovery point of view, oil and natural gas is where it is because it ended up there through millennia, through natural traps. So if the oil and natural gas is stored safely in certain reservoirs throughout the world, There's no reason why CO2 and other fluid can't occupy those same voids. So there are economic issues with respect to carbon capture and storage. There certainly are some technology hurdles that still remain, but at the end of the day, there's a tremendous amount of confidence on the technology, at least I think. In terms of policy, it's important to keep in mind that the federal government, even under the Obama administration, identified carbon capture and storage as a key carbon mitigation that sources could use for compliance purposes under the Clean Power Plan, and indeed under any suite of climate mitigation programs under the Clean Air Act. So the Obama administration said, to be continued subject to potential changes by the Trump administration, that when you're capturing CO2 and injecting it underground and indeed producing additional oil, that qualifies for compliance purposes. So that federal policy is still in effect. There's also federal tax incentives like 45Q. If you're injecting CO2 and using it for enhanced oil recovery, the capture facility under current federal law gets $10 a ton. If you're using it, if you're storing it in a non-EOR reservoir, you get $20 a ton. So the federal policy is very clear and in favor of this technology. And indeed, going back internationally, under the days of the Kyoto Protocol, and we all know the Kyoto Protocol expires in 2020, the international trading mechanisms of the Kyoto Protocol also acknowledged and approved carbon capture and storage as a mitigation technology. Now, there weren't any projects approved under that methodology, but even the Kyoto Protocol individuals believed that this technology was valid. And lastly, I just want to close talking a little bit about the importance of carbon capture and storage to the region. So Colorado does sit where all these projects are going on, or many of them are. There are projects like this in terms of EOR in Wyoming. To your south and southwest here in the Permian Basin, this CO2 enhanced oil recovery activity is going on. There is an existing CO2 pipeline network that runs right through Colorado into Wyoming, down into Texas. So many people think that this is the region where these projects are going to continue to prosper. And indeed, on behalf of the University of Wyoming, I'll say we're quite happy because we're currently chasing 2 Department of Energy carbon capture and storage projects under a program begun under the Obama administration to try to achieve CO2 capture in a retrofit way from existing coal-fired power plants and utilize that CO2 in an economic way. So this technology is vitally important from a research point of view, from an economic point of view, from a job point of view, and from an energy point of view for this region. And that concludes my remarks. Mark, thank you very much.
Thank you, Kip. Next, we'll hear from Larry Baxter.
It's a great pleasure to be here, a great honor to be here. I've met and spoken with the people on this panel on several other occasions and have a high regard for them. The 3 of them have a great deal of wisdom. You're lucky to be able to have them here. I want to start, before I start with my slides, I'm going to start with a very positive message, move to a very discouraging message, and then come back to a positive message. If you look at the history of the United States, go back to 1970 when we got serious about the environment, passed the first version of the Clean Air Act, and so shortly after that, most of the rest of the environmental regulation in this country. Since that time, this might surprise you if you're not in the environmental statistics area. Since that time, we have reduced in absolute terms, not in per person terms, but in absolute terms, the total amount of pollution that's being emitted in this country by over 75%. So the environment is being abused 75% less now than it was in 1970. I see people shaking their head, but so those are the EPA statistics of if you just take all of this stuff together. And that's an incredible accomplishment, and that's been accomplished with a lot of people not working cooperatively almost ever, trying to get to work through these environmental regulations. In 1970, if you had told people that you could do that and at the same time doubled the population, tripled the number of miles that we drive in automobiles, doubled the GDP, that's an astounding technical accomplishment. So that's the good news. So we think sometimes of CO2 like another pollutant, and so let me help you understand, first of all, there is another technological, but that was just a warm-up act for what CO2 is going to take. There is every reason to believe that CO2 is going to be a much more difficult challenge than the sum of all of those other pollutants. And I'll go through that in just a minute. And just to hit some statistics, if we are to accomplish the 2 degrees C goal that we have to control the climate within that temperature band, we need to capture about twice as much CO2 as the sum of all of the CO2 that is currently being emitted in association with power generation. So if we capture 100% of power generation CO2 globally, we're about halfway toward that goal. So, that's an astounding amount of CO2. The quantities that we're talking about are mind-boggling. So if you go back to a typical power plant and think of the other pollution control devices, the impact on the power plant on an energy basis is less than 5% in terms of all of the energy that gets invested in a power plant to do sulfur, NOx, particulate, and the other kind of controls. CO2 alone will reduce the efficiency of a typical coal-fired power plant by something like 25 to 30%. And so that's a much larger impact. And it doesn't have to be, and I will show you in a minute that there's good reason to think that it can get cheaper than that, both energy-wise and economic-wise. But this is a really big problem. This is a bigger problem than almost anybody can imagine. So if that sounds discouraging to you, let me come back then to the hopeful message, and this is where I'll start here. I truly believe that this is, well, let me make one other point. The cleanest environments on this globe all are associated with countries that have robust economies. And if we do something in an effort to address environmental regulation that destroys the economy, we are probably going to remove the social ability that we have to address issues like environmental change. If you look at the most polluted countries on this planet, they are all countries who simply don't have the social capital to do something like environmental issues. They're still trying to keep people from starving. They're trying to address health effects. So the economy is important. We can't simply ignore the cost of these things. The cost is a major driver. And in fact, I would argue that the cost is the biggest driver because it's the coupling of cost with the economy, with environmental regulation that has driven almost everything. And on a kind of a separate issue, but the number of people that have moved from abject poverty in this world to a middle class in just the last 20 years is twice the population of the United States. It's the greatest global economic progress this world has ever seen. But it's 100% due to economic alignment with people, mainly in Asia and Southeast Asia. And it has so prior to this last economic development in Asia, there have been all kinds of humanitarian organizations that wanted to effect this kind of a change, but by comparison, they've been very ineffective. The effective change has come by coupling the economy with that goal. And if we can do the same thing with environmental change, we have a very promising thing. So let me go through talking about, I think that this is a problem that is at its core, the CO2 issue is at its core technical. If we can find technical solutions and if we can focus on finding those technical solutions, then everything else will line up. And there are technologies that are rapidly maturing that will address this issue very effectively. They are rapid and expensive. They also provide energy. But one of the things that we have to do is get out of this mindset it's either renewables or fossil. We've got to find solutions that work for both renewables and fossil energies and enhance the capabilities of both. And those are happening. And so let me just go through some of these slides now. First of all, primary energy utilization. This is in the United States. We actually are decreasing our CO2 emissions in the United States, have been for some time now, and globally they've actually stagnated, or arguably slightly decreased, but within the noise of the calculations. But that just means the emissions have increased. The concentration of CO2 in the atmosphere is monotonically increasing, and we have really not slowed that down at all. We just slowed down the rate at which it's increasing, but we haven't slowed down the increase. If you look at the global primary energy utilization, you can see some hopeful things with renewables toward the bottom there. But when you consider the magnitude of those renewables and look at the magnitude of the fossil energies, which are all toward the top, You can see that fossil energies are large and they are increasing rapidly on a global scale. And there's actually lots of reasons having to do with intermittency and other kinds of issues that it's hard to imagine that they will ever be completely displaced, at least in even our grandparents or our great-grandchildren's lifetimes. So we've got to find a way to address the environmental impacts of fossil energy if we're going to have any hope of solving this climate change issue. We in addition to that, should be embracing renewable energies to the maximum extent, but we should recognize there's a limit to what renewable energies are going to be able to do in this problem. The costs associated with carbon capture are summarized here. There's lots of people that have tried to estimate these, but if you look at just the first couple of bars, on the left is the cost of generating electrical power from a typical coal-fired power plant broken down into its several components. And the bar next to that is what that power plant would cost if you were to build it with a carbon capture technology. And as you can see, the costs of electrical power generation increased by about 80%. And that's true for a wide range of technologies that we look at. So the energy impacts and the costs can be fairly significant. And the experience that we've had is that the energy impacts are about what I quoted before. That's been the experience. The costs are actually higher than we would anticipated. I guess we would have known they would have been higher in the first few instances. It's always more difficult with build serial number one of anything. But the costs are still manageable. This is the required reduction. This is just one projection from people who think, I think, clearly, but also realistically about these things, about where CO2 emissions will go. But the most important thing to recognize on this graph is that the emissions reduction will require as much CO2 removal from emission right now, or reduction in emission, about twice as much as the total amount that comes from power generation, current power generation. Just one slide. This is some of our own technology, and I don't mean to co-opt the meeting to talk about it, but this just illustrates the possibility of other alternatives. So on the left are the costs and the energy consumption of current technologies that we're trying to do carbon capture. And what you can see in the other two bars on the right are the kind of a simplified application of a very promising technology that we're developing, roughly half the cost and half the energy consumption. If we integrate that a little bit into the power plant, we can reduce those costs and the energy even further. But the point of this slide is that we can get to about half the current costs. Those are still large costs, and they're still large energy demands. They're going to be much larger still than all other pollutants combined. But this is about the limit. There might be several ways you can get to this level of cost and this level of energy, but theoretically we're within the practical range of what you can get to in terms of the theoretical amount of energy that it would take to do this capture. That is, these numbers are about 70% above the theoretical limit, and practically it's really difficult to get much closer to that theoretical limit than that. So the hopeful message is there are technologies being developed, and they are effective. They actually enhance renewable energies through energy storage technologies that come along with them. They make renewables much more effective in terms of the way they can deliver energy. They reduce the carbon footprint of fossil energies, and there are technological solutions, but they're not going to be free. They will represent about a 2 cents per kilowatt hour increase in our electrical power bills. They will increase the energy consumption at a power plant, but those are pretty manageable costs. The range of electrical power costs right now is much larger than 2 cents per kilowatt hour from region to region in the United States. So the market should easily be able to absorb a 2 cents per kilowatt hour cost of increase without destroying an economy or causing chaos or the world to end, as some people anticipate it might. So.
Thank you, Larry. So I'm going to ask a few prepared questions, and then we'll open it up to the audience. We have about 19 minutes left, so I'll try to split that time equitably. My first question is for the panel, and I wanted to explore a little bit the Paris Agreement, which was adopted in December of 2015. It's the most aggressive global policy mechanism for reducing carbon dioxide emissions to date. In it, each country determines, plans, and regularly reports its own contribution it should make in order to mitigate global warming. So my question is, if all the participating countries adhere to their commitments, how far does it actually go towards limiting global temperature rise? And you can answer in order, or anybody who wants to jump in first.
It says it's on, there it is. Probably the best answer is not far enough. I don't think anybody believes that even compliance with the Paris Accord would have solved the climate change problem. And so the magnitude of this problem is staggering. The Paris Accord is a very aggressive accord. At the time that people signed it, I'm pretty sure that it was more aggressive than most people thought would have ever gotten approved at a meeting like that. But it's still not, it's not enough to address the climate change, but it's a significant step and would have been a significant, maybe still will be a significant step in that direction. I will add parenthetically, though, that the progress the United States has made to date on CO2 reduction, and we have made progress on that reduction, I'm pretty sure that my panelists would agree with this, has almost nothing to do with regulation, and has had everything to do with the price of natural gas and the shift from coal to natural gas. And that price of natural gas, anybody that tries to project anything in the future in energy is just inviting themselves to make a fool of themselves. But there are lots of reasons to think the price of natural gas is going to stay low for a while. And we will probably continue to make progress despite the apparent lack of any agreement or any us pulling out of this Paris Accord. There's at least some reason to think that we can continue to make progress on CO2 reduction, mostly through economic drivers.
So I will just agree with Larry. I know, and I can't quote the figures, but there were several analytical groups that assessed the so-called INDCs, which were what the country's submissions, their commitments under the Paris Agreement, and analyzed what the reduction would be. And I remember the most recent version of those that I read was about a year ago, and they said if all the country's commitments under the Paris Agreement were fully implemented, it would have a negligible impact on the ultimate goal of the agreement. But that doesn't mean the agreement is unimportant. It certainly sits out there as a critical policy vector, but you're right. If you were looking at it just quantitatively, the Paris Agreement is not going to do much based upon the commitments made to date.
I'll add a little bit here. I think, a policy vector is a really good way to put it, being that. But the other question is, if we're, again, to prevent 2 degrees C warming by 2100, and it was even a little more aggressive than that, there was a path to prevent 1.5 degrees C warming. I think the question that we should ask is, well, what path would that look like to get there? What would it take? Forget about, what everybody's agreeing to do, but what does the path actually look like? And I think the important consideration is absolutely mitigation on a larger scale than we're doing today in terms of preventing CO2 emissions in the atmosphere in the first place. But then, again, those aggressive targets require negative emission strategies. I mentioned bioenergy and also direct air capture, but other more affordable approaches, low tillage of soils, preventing deforestation, afforestation, all of these strategies could be implemented. And those are strategies that countries that are still worrying about healthcare issues, global GDP, and things like that could have an impact on, especially in terms of land management practices. So I think the question one has to ask is, what does the path look like? And it's going to be different for different countries.
Okay, so that actually answered 2 of the questions that I had. So let me go to one that I think is really important and maybe the most important one, and that is public opinion to date has been decidedly negative towards higher energy costs and carbon capture and storage activities in their backyards. How do we overcome those obstacles if we're going to successfully implement commercial scale solutions?
I think public opinion is fairly, well, carbon capture and storage is not nearly as popular as it used to be. I think that's a safe thing to say. But most of the, if you look at IEA and the Global Climate Project and people like that, they all recognize carbon capture as an essential, not just a potential, but as an essential component of any realistic goal to try to get to a stable climate. So I perceive that the technical challenges and costs are much, much greater in the separation preparation stage, what we call the capture stage of this process. And I think the storage stages are technologically much more developed. But I also think that the storage stages have probably the largest public perception barrier to overcome. And I think that's going to be a significant barrier. You need to convince people that you can store something in underground for 100 years approximately is how long it has to stay stable in order to get before it absorbs into the local environment, and that it's not going to come rushing back up. And there are horrific but well documented stories of natural CO2 releases from places that will scare anybody if you look at them and think the potential of this happening near my community or near something I care about could be horrible. The reality is that potential is very remote. There is almost no chance of that happening, but that won't be easy to get the public to accept that, I don't think. So.
Yeah, I would just add to that, and obviously public acceptance is key. If the mayor of City A opposes a technology, then that technology is not going to be deployed. I would also say that there's no such thing as a free lunch. There's opposition to wind farms. There's opposition to, building a Dunkin' Donuts. I mean, every energy system will have some opposition, and I think that solving that issue for carbon capture and storage will just be the next thing. I do think it's also possible that this is a technology that's not going to be deployed everywhere. There probably is not going to be a carbon capture and geologic storage system in downtown Cambridge, Massachusetts, but these systems are likely to be deployed, quite frankly, where they are now, around existing oil and gas operations, around existing CO2 pipeline networks. In the vicinity of communities where drilling into the subsurface to produce oil and natural gas and oil is as common as going to McDonald's. And just to emphasize Larry's point, there is tremendous confidence on the geologic side about the storage attributes and its security and safety. Now, that's not to say that there will not be public opposition to it, but I think the technology will ultimately provide the necessary comfort in those communities that choose to allow these projects to go forward. And again, these projects aren't coming to people that don't want them. They will grow organically, I think, from communities that want them and need them, and they recognize the role that fossil energies will continue to play.
And I would just agree with them. And I'll just make one brief comment. I think it's important in terms of education and public perception to recognize that oil and gas has been stored for millions of years, and we're looking at storing CO2 in those depleted reservoirs. And the same trapping mechanisms that were there to trap oil and gas will presumably be able to trap CO2 as well. I think, one thing that needs to be recognized is that, in the regions in which this is done, that the characterization of the subsurface is well known, and also that the well logs are well known too, so that you don't get CO2 coming up unexpectedly in an abandoned well, for instance. So being able to understand the geology and understand the history of those sites is key, but that's all work that's being undertaken, and the key is to just have more of the demonstration scale efforts that we have today. I mean, we have just a few in North America that we talked about today, and we need 100 or hundreds of those same kind of efforts.
Okay, thank you. So I want to thank the audience for sitting patiently and waiting for this moment. You now have the opportunity to ask questions of this group of experts. Maury, is there a microphone going around? Or? I don't have any that have come in, so. Okay, so let's start right in the front.
Thank you very much for everything that you've said. Am I on? Nope. Am I on now? Okay. Thank you for all that you've said, particularly this last piece. It occurs to me that this is a pretty sophisticated audience, and you're explaining things in a detail that I don't think the average group would understand. So to your point about public perception, how can I be a good voter if I don't understand the issues, if I don't understand the technology? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a good voter if I don't understand the issues? If I don't understand the technology, how can I be a So what part of what you're doing has the ability to market actual information in an age where people are very suspect of things that come from government entities? What do you recommend that we do to market facts so that it can have an impact on policy?
So I will take a run at that, and it's a great observation. I might even quibble with your use of the term marketing. I think at the end of the day, you're presenting facts to the best of your ability to potentially impacted communities, and I would say those communities have veto authority over any particular project. I will say for areas of the country in which this research is being done, there has been a fair amount of public outreach work already undertaken. So the U.S. Department of Energy, for example, through its regional partnerships, has been trying to advance with some success, some not so success projects with public outreach components as key aspects of them. In the next iteration of this Department of Energy program, we're pursuing 2 project sites in Wyoming, and under our grants, our federal grants, we have to advance public outreach plans where we have to lay out in great detail that we will be meeting with the commissioners of X county, we will be meeting with the mayor, we'll be going to the citizens of whatever the city it is, and this would be a years-long process, but everybody understands that these projects are not going to go forward without the consent of potentially impacted citizens. And I guess from my world where I see these projects going, that effort is underway, but I think in communities where this maybe is less relevant now, you may not be seeing that. But I'm otherwise completely in agreeing with you. And again, to me, citizens have veto authority over these projects, as well they should.
If I could add one thing, in a much broader picture, I find the discussion of climate change as one of the most discouraging technical discussions I've seen develop in our country. I don't know how it became so politicized and so personal, but it's a sign of our times. There's very few things we discuss nationally right now that don't have that character, and I don't pretend to understand why. I do think that the solution is for all of us to recognize that all these voices have merit, and we need to, as the panel before us talked about, listening to people who disagree with you and understanding what they're saying and understanding why they're feeling the way they are is a art that we're losing in our society. And I think there's an arrogance that comes from professors like myself that people are reacting to that I can understand where they're coming from. And I think to the extent that we can listen better and try to understand people, try to factor all of these things into our policies, that's the only way forward that I can imagine. So.
And while the microphone is going to the next question, I'll just say that I've spent maybe 20% of my time over the last 10 years talking to Rotary groups and high school classes about the issue. And I empirically have discovered that you need to be able to talk about it at about the 9th grade level, regardless of who you're talking to, because it is a highly technical field, but we have to get it into the public school systems to make a difference in the future. So, next question.
Is it okay? The news, this is really appropriate because the news that came out today, and it was from BBC that I saw that the World Meteorological Organization has reported that CO2 levels for 2016 surged to a level that we haven't seen in 800,000 years, which went from 400 to 403 parts per million. And I think they really support what I hear you saying, that those, even more so, those global temperature targets are unattainable, and they're combining it with the El Nino event as well as human activity has caused that surge. So that adds to more of the depression that we're hearing about CO2. Can you comment on this latest news and does that change anything for you, or? Yeah, thank you.
I'll make a quick comment. I heard listened to the same news broadcast. So it's true that the CO2 level in the atmosphere is much higher than it's been over any period of, certainly comfortably we could say, in any time that we could say we had a society here on Earth. That is, social structures where people collectively try to accomplish things. So I view this as the biggest challenge we have, frankly, right now. I think it's that big of a technical challenge. But I also have to say that it is common for politicians and the press to unjustifiably attribute things to climate change where there is no science, and the scientists wouldn't agree with what they're saying. But people, you see an individual hurricane, for example, it's just wrong to attribute a lot of the things that we see. So, for example, let's go through the drought and then the water that happened in California. If you listen to the climatologists, that was not driven, well, the drought itself was not driven by climate change. The fact that the climate had dried the soils and the soil was therefore less capable of absorbing water did drive a little bit of the drought. But if you listen to the scientists, they often are not in agreement with a lot of the extreme things you hear in the press. And I think we get a lot of policy and press announcements that aren't sufficiently vetted through a technical community. And that's part of, I think, trying to keep a clear head about these things. But I'm not in any way diminishing the importance of climate change. Climate change is the biggest issue, I think, that we will face in this century, perhaps. But that doesn't mean that everything can be blamed on climate change. So.
Let's take one more question really quick. The woman in the green, yes.
Are you saying that the warmer ocean is not allowing more moisture to go up? Therefore, we're having these rains like 30 inches in a day? That's not due to climate change? Did you just say that? And the other, I'd like to say that we have the Koch brothers who are telling our president that the climate change is funny words, et cetera. So this is our problem, is please vote. Please vote. Your vote is important.
So, yes or no answer, is that what you were saying?
So I'll try to be as brief as I can. So if you talk to the if you look at the statistics of hurricanes, and if you talk to these agencies who track those, they will tell you, even if you look in the reports that come from the International Panel on Climate Change, they will tell you that there's no correlation between climate change and the number of hurricanes. Now, there are good physical reasons to think that might eventually happen. But as of right now, they say that the cost of hurricanes has increased dramatically. But that has a lot more to do with more people living on the coast, and therefore much more damage being done when hurricanes do come ashore than it does with the actual magnitude of the hurricanes. So the statement in the last document is that neither the frequency nor the intensity of the storms can be correlated with CO2 emissions to date. So,
Thank you. Join me again in thanking our panel.